hi everyone. My name is Susanne Claus. I am from the French National Aerospace Research Center called ONERA, where I'm a researcher. And I'm going to talk about today about the Cut Finite Element Library for FEniCSx that I'm developing. So this is not the first incarnation of a CutFEM library that I'm developing. It's basically the second one. I did develop already one for FEniCS and now for FEniCSx. So as you may have, you may have already seen this morning in the tutorial session the kind of methods that I am working on. So I'm working on methods where I do not discretize my geometries with the finite element mesh. So I have a geometry description on the one hand, and then I have a finite element mesh on the other hand. Usually, or very often, I use ruler. Oh, what does this do? Oh, wow. Very often I use level set functions to describe my geometries. So in case you're not familiar with level set functions, it is a functional description typically on the background finite element mesh that is 0 on the boundary of the object. And the particular cut or unfitted finite element methods that I am working on is the type where I integrate, especially in the cells that are cut. So I take my geometry description, I embed it into the finite element background mesh, and then I cut along the boundaries. And in order to do this accurately, I need to introduce quadra rules that now vary from element to element through this cutting. So instead of one tool, I developed 3 different packages, essentially, that reflect a little bit this workflow. So 3 different modular components. The first component is cut cells, which does intersection routines, typically between level sets and different mesh cell types, and also generation of these quadra rules. So what you've seen on the first slide, the geometrical intersection. This is a tool that's independent of FEniCSx. And then I have 2 FEniCSx extensions. One is called run-in-gen, and this is an extension of the form compiler, which generates integration kernels for these runtime rules. Why this is necessary, I'm going to comment on. And then the hard piece, CutFEMx, which is a DolphinX extension. So I'm going to now show you in different slides these different components and what they roughly do. So the first one is cut cells. So that's a C++ core library that has a Python interface with nanobind, and has very, very few dependencies. So it does not depend on FEniCSx, and it's licensed under MIT license, and essentially it uses lookup tables a la marching cubes in order to compute intersections very efficiently, and then generates quadra rules. And these quadra rules, they are then used by this extended form compiler. This form compiler generates runtime integral kernels that then pass the quadra rules and any other data that is needed on the unfitted interfaces through custom data since FEniCS 0.10. So typically, I mean, here you see some very rough snippet that passes the custom data and then unpacks the quadra rules inside. And this is what this generator does. So and why do I need this generator? That's because typically in FEniCS, FFCX generates integration functions or integration kernels that pre-evaluate the shape functions and their derivatives. That's very important for efficiency because normally this is the same in every cell. So it's a lot of additional work to evaluate them. But in my case, when I integrate only over parts of cells, I then need to evaluate always in different cells the shape functions and their derivatives. So in that case, I need a different code generation that keeps this information alive and evaluates the shape functions and derivatives. So this is the code generating part. And then I have the CutFEMx library that then puts everything together and also communicates with DolphinX. So that takes the runtime quadra rules that are produced by this geometric library then does an assembly over the integration kernels, including the runtime rules, has different cell classification functionalities, and also some visualization support so that I can take a function on the entire mesh and cut it back onto the different domains. So now, in the last few slides, so all of these tools, they are released under MIT licenses, so you can find them on my GitHub. And now I also have written a documentation and some tutorials, which I can show you later in the software session to explain it. And now I'm just going to do a very quick walkthrough to show you how it works with CutFEMx. So at first, here I define a level set function in the typical FEniCS manner. So I use some numpy and x0, x1 to say x and y for my function, for my level set function in x, y, z. Then I interpolate it onto a function space. And then I can take this interpolated function and cut my mesh with it. And then I can query it for different parts of the mesh. So this first one there, locate entities, will give me all the cells that are fully inside my level set. So that's the green cells up there. That's inside cells. And then it can query different quadro rules, inside quadro rules on the interface, and also some functionality for stabilization. In this case, ghost penalty facets. And what I then do is that I pass these through subdomain data to the UFL measures there. So you see this definition of UFL measure. So that's the standard measures dx/ds, but with a special subdomain data where I pass the quadro rules into. And then I can write my weak formulation in UFL, very close to the mathematical formulation in a quite natural way. Okay. Then invoking the form, the special assembly for the moment, and then one more functionality where I have shortcuts where I can pass a form that then analyzes what I integrate over to deactivate everything that is outside the domain. This is practical if you have moving boundary problems where this domain might not stay fixed, but it moves. Otherwise, it's probably better to create a sub-mesh of what you're working with. But in this case, if you have moving domains, this deactivation is very handy. And this shows the catted solution, basically. Okay, there's just some images. And if you have any further questions or want to see some examples, come see me during the software session. Thank you.
Thanks for the nice talk, and you were in time. That's great. Congrats on that. Any questions from the audience? Yes?
So, can you apply this to cohesive elements in fracture, for example? Because to describe interface, do you have application in this sense?
Yes, yeah, that's possible. Through the, because I have a handle on these quadro rules, on the interfaces, you can use Nietzsche to describe some form of cohesive elements.
You can have a jump.
Yes,
the
yes.
crack,
I can have a.
Can be not on the edges.
Correct. Yeah, that's possible.
Yeah. Any other question for Susanne? Yes, Jack.
So FEniCS now supports quads and hexes, and do you plan to add? Because I know it's very difficult, right? Do you plan to research this problem of intersecting and doing?
I have it working for quads and hexes. Yeah. Because this is
how is it done?
through the geometry. Through the geometry backend. Here you see an example of where I cut through a hybrid mesh with quads in this case, but I have hexes as well. Maybe this was hexes.
Self-triangulate?
Yes.
Okay. That's very cool. I didn't notice that. So.
Ah, good. Then we learned something new.
Yes.
If you were to apply this to multiscale mechanics, so for example, you have inclusions in the matrix and whatever, can you do some local refinement, or are you stuck with the background mesh?
No, you can refine the background mesh.
And also, yeah, but then not locally, right? And then somehow the idea gets lost, or?
You mean now in a non-conforming sense? Then you need some additional.
No, not necessarily, but you have stress concentrations around your inclusions.
No, but you can refine. That's
Okay.
your background mesh can do as well. It's independent, so you can zoom in on some values in the background mesh.
You could have any background mesh.
Yeah, I can have any background mesh. It doesn't even need to be structured. I mean, these examples are structured because they're easy to set up, but it doesn't have to be structured. There's no assumption of it being structured.